number of views of the of every video in the I can realize only a few are revising. And also one more thing, that only 4 or 5 of you have not accessed your LMS portal. So it is recommended because within 72 hours your first exam will be there. So I would recommend you to access your LMS portal and also practice that whatever I have given. Okay, only 4 people are there, those who have not accessed. Okay, I don't want to take the names, okay, in front of your class. So those who have not accessed, they know. So if you are listening, please access your LMS portal so that you don't face any problem during the exam. Okay. Out of these 75 students, only 6 students have attempted the quiz. Okay. So it is better for your betterment. I have given the mock quiz. That is practice quiz I have given. Okay. So before attempting the exam, you can practice for this quiz, and this quiz will be available today up to 8 p.m. Okay. So before facing the real exam, you can try it so that you do not face any problem. Okay.
Sir, can you extend the quiz for tomorrow 8 p.m. like after the exam we would give an attempt?
After the exam?
The physics exam, sir. After physics we are having math.
Okay. So you are having any exam today?
Tomorrow we are having physics, sir. Day after tomorrow we are having our math exam.
Okay. So I will extend that time.
Yes, sir.
Okay. Then let us discuss today's topic, that is quadratic form. Okay, is it visible?
Yes, sir.
Okay. So far we have discussed that there is a quadratic form. So what is a quadratic form? Okay, no, not we are just recalling our last class. So in order to recall our last class, that if A is a real symmetric matrix, then that we have seen that the transformation that P will be a orthogonal matrix. For orthogonal matrix, we have seen that P transpose is equal to P inverse. Just a minute. Okay. So now we will discuss today's topic, that is quadratic form. So what is a quadratic form? Okay. So actually, quadratic form is a polynomial, homogeneous polynomial of second degree, okay, in any number of variables. Suppose 2 variable quadratic form, we will write it q of xy, 2 variables x and y, then the variable will be this way. Okay. And 3 variable quadratic form will be 3 variables x, y and z will be there, and then some mixed xy. This was supposed to be cut down 2 times, it is there. Sorry for that. So, and 2 times of mixed terms of yz and zx will be there. It can be also in 4 variables. Okay, not only 4 variables, it can be n variables. So for n variables, we will write that quadratic form of this one. Okay, x1, x2, xn. It will be this way. Summation I equals to 1 to n j equals to 1 to n aij xi and xj. So that is a quadratic form in n variable. Okay. Now from this quadratic form, we will have a coefficient matrix. Coefficient matrix. The coefficient matrix of this quadratic form, how to find it? Suppose there is a quadratic form, okay, u of xyz is given as ax square plus by square plus cz square plus 2h xy plus 2g zx and this is 2f yz. Okay, if the quadratic form is given like this way, then in order to find the coefficient matrix A, this will be called coefficient matrix of this quadratic form. Quadratic form, then it will be like the coefficient of that A11 position will be coefficient of x square. Then A12 will be the coefficient of xy. Similarly, half of the xy term. Okay, this is how we will find the coefficient of the quadratic form. Okay. In order to realize one more fact, that suppose x is there, y is there, and z is there. Similarly, if x is there, y is there, and z is there, then x times x, that is x square. So here A11 position will be the coefficient of x square. Similarly, x times y, that is y. Again, because we are having y times x, so xy will be again one more term will be there. So that is A21 position and A12 position. So this coefficient will be divided. Okay, they will take the equal part of the original coefficient. So half of this coefficient. Similarly, half of the coefficient of zx, because x times z. Okay, and this way we'll do the other computations. Okay, so the matrix will look like this way. So half of this. Okay, so if you look at the matrix, it will be in this form. Okay, so this is x, y, z, x, y, and z. So x square having a, the coefficient is a. Then xy, the coefficient is 2h, so half of 2h is actually h. So h is there.
Sir, screen is not visible, sir.
I think, how about others? Is it visible to you?
It's visible for us, sir.
Yes, sir, visible, sir.
So can you help your friend? Just type on the chat box what to do and how to do.
Just pin another screen and just unpin.
Okay, okay. So similarly, we'll take the coefficient of xz, half of xz, half of 2g. Okay, so it is z here. Similarly, other coefficients. Now we can see that this is a symmetric matrix. Okay. So the coefficient matrix of a quadratic form is always a symmetric matrix. Okay. This is a symbolic matrix. Let us take one real matrix. Suppose the quadratic form in 3 variable x1, x2, and x3 is given as this way. Okay, so if you write it according to this formula, then the coefficient matrix will be, this is a coefficient of x1 square 1, half of the x1, x2, that is 2, half of x1, x3, that is 3. Similarly, half of x1, x2, that is 2. The coefficient of x2 square, it is 4. Then half of x2, x3, that is 1. Similarly, half of 3, then half of 1, and that is 6. So if you just rewrite it, you will get this one. Okay. This matrix. Okay. For given a coefficient matrix, we can find the quadratic form. And for given any quadratic form, we can find the coefficient matrix. Okay. Okay. The use of quadratic form is actually tremendous. There are so many applications of quadratic form. So that is why it is very, very important. If you study in the 7th semester, there is a called optimization technique. Okay. Those who are in the computer science department, those who are having optimization techniques, then they will find this is very useful. This quadratic form is very useful. Okay. So in the example 1, it says write down the quadratic form of the corresponding matrix. So what we have to do here, we take one column matrix x1, x2, and x3. We take the transpose. It will be x1, x2, and x3. So we'll substitute. Okay, we'll multiply x transpose A and x. So if we write it here, x1, x2, and x3, then A matrix, and then column matrix x1, x2, and x3, then you will get this relation. Okay. So from here, if you just do the matrix multiplication, this is 1 cross 3, this is 3 by 3, and this is 3 by 1. So the dimensions are matching. We can do the multiplication. So this will become a row matrix, and this is a column matrix, 3 order 3. So if we just do another multiplication, matrix multiplication, we will get the quadratic form. So this is our required quadratic form. Okay. Okay, right. Now we have to find the canonical form. So how to find the canonical form? It's canonical form of a given QF quadratic form. Okay. Suppose A x square plus B plus C z square plus y G z plus 2f this yz. Then we know that the coefficient matrix A is nothing but A T H B F G F and C. We'll write down the characteristic equation. From here we will get lambda 1, lambda 2, and lambda 3. Okay. After this, what we will do? We will find out Ax equals to lambda 1x. Okay, we will find out Ax1 into lambda x1. From here, we will find out x1. Okay, one column, one eigenvector. Okay, this is x1, y1, z1. Similarly, from ax to lambda to x2, we will get x2 as another eigenvector. And from ax3, lambda 3x3, we will get eigenvector as this one. Okay. Since this is a symmetric matrix, okay. In the last class, we have seen that the P matrix, the modal matrix, P, if we take this one, okay, after normalizing, okay, after normalizing, if we take the P matrix, okay, just a minute, where is it? Okay, so we have found from A, we have found lambda 1, lambda 2, and lambda 3. From here, we have found this is x1, x2, and x3. Okay, this is we can find for any matrix, whether it is symmetric or not, we can find it. But if it is symmetric, if symmetric, okay, if A is symmetric, then these eigenvectors are orthogonal. In the last class, we have seen this one. And if the length of these vectors are not 1, we can define, we can make the length as 1. Okay, so that they will be orthogonal and the length will be 1. Okay, and alpha 2. So this will be, this is length. Okay, alpha 3. Yes. Okay. So if we define the modal matrix as alpha 1, alpha 2, and alpha 3, then we have seen that this modal matrix becomes orthogonal. Orthogonal matrix. For orthogonal matrix, we see P inverse equals to P transpose. Okay, so given a matrix, A, okay, by diagonalization theory, by the concept of diagonalization, we have seen that we can find P inverse AP is a diagonal matrix, or we can write it number 1. lambda 2, 0, 0. Okay. And this transformation is called congruent transformation. It is also called orthogonal transformation. And this form, okay, for any, we have seen, for any given quadratic form, we can find the coefficient matrix. Okay. And for any given coefficient matrix, we can find the quadratic form. Okay. So now, if this is the quadratic form of a matrix, this is a coefficient matrix of a quadratic form, then we can write, okay, then we will be able to write that for any non-zero matrix x1, x2, and x3, we'll find out x1, x2, and x3. So if we want to find the quadratic form x transpose b and x, then what will happen? This is x1, x2, and x3. So after that, we will have D is a matrix. We will have x1, x2, and x3. Okay, so from here, we will get lambda 1 x1 square plus lambda 2 x2 square plus lambda 3 x3 square. Okay, so this is, okay, known as sum of squares. Sometimes it is sum of squares, or we will call it canonical form. Of the quadratic form. Given a quadratic form, okay, given a quadratic form x equals to x transpose ax, we will find, okay, from this matrix lambda 1, lambda 2, and lambda 3, since the quadratic the coefficient matrix is always symmetric for a quadratic form, okay, it is symmetric matrix, so we will find the lambda values and the eigenvectors will be always orthogonal. From here we will find the P matrix. Okay, we will make it alpha 1, alpha 2, and alpha 3. Alpha 3. From here we will find P matrix 1, alpha 2, and alpha 3. Okay, and this will give us that P inverse AP equals to D. Okay, from D we will get this. Okay. So this is, and this P matrix is called, this P is called, okay, it is this P is called matrix of transformation. Okay, this is called canonical form. okay, of quadratic form of the given quadratic form, and this is called orthogonal transformation or congruent transformation. And this P matrix will be called matrix of transformation, because with the help of P, we are getting from this to this. From this Q, we are getting this canonical form. So we'll see with an example. Okay. Suppose, okay, whatever I have discussed so far, it is actually written here. So I'll directly go to the example. I have discussed these things already. Okay. So the matrix is given as this one: 3x square plus 5y square. 3x square plus 5y square plus 3z square minus 2yz plus 2zx minus 2xy. So if you rewrite it, 3x square plus 5y square plus 3z square minus 2xy plus 2xz minus 2yz. So the coefficient matrix will be, okay, A11 will be 3, A22 will be 5, and A33 will be 3. Then this part will be the half of minus 2. This will be half of 2. So this will be half of minus 2. Similarly, this is half of 2. And these are half of minus 2. Similarly, this is half of minus 2. Okay. So the matrix is always symmetric. So the matrix will be always symmetric for a quadratic form. Okay. Now we know how to find the A minus lambda I equal to 0. After solving this characteristic equation, we'll find lambda 1, lambda 2, and lambda 3. Okay. Since this is a symmetric matrix, it's x1, x2, and x3 will be orthogonal. But the length may not be 1. So we'll make the length as 1. Okay. From this, we will get the P matrix, matrix of transformation, alpha 1, alpha 2, and alpha 3. Okay. Okay. So matrix of transformation, because P is an orthogonal matrix. P orthogonal matrix, so P transpose will be P inverse. So we can easily find P inverse AP, and we can verify that this will be the diagonal matrix, where this diagonal is nothing but the lambda 1, lambda 2, and lambda 3, all are zeros. Okay. And the canonical form will be, this is lambda 1 x square plus lambda 2 y square plus lambda 3 z square. Okay. So in place of lambda, we'll put the particular values. This is 2, this is 3, and this is 6. Okay. So this is how we'll reduce given a quadratic form to its canonical form. and we have to specify that the matrix of transformation. So this is nothing but the orthogonal matrix with the help of eigenvectors. Okay, so that is how we will find the quadratic form. Now there is another concept. It is called nature of the quadratic form. Okay, the nature of the quadratic form. What it says, if we have a quadratic form Q, this is Q of x1, x2, xn, then this quadratic form is said to be positive definite if all the eigenvalues of A are greater than 0, strictly greater than 0. It will be called negative definite if they are all negative, strictly less than 0. Okay, positive semi-definite, the third case, if all are greater than equals to 0. That means all will be greater than equals to 0, but at least one of them 0. And it is semi-definite if all are negative, at least one of them is 0. Okay, so indefinite if some of them are positive and others are negative. So in the first case, you can see that all the eigenvalues are positive. So here it is case 1. For case 2, we can see this is a 4 by 4 matrix. Also, this is a triangular matrix. Okay, lower triangular matrix. We can have upper triangular matrix also. For this type of matrix, okay, for this type of matrix, the characteristic equation will be lambda minus lambda, this one minus of this one, that is minus of minus is plus. Okay, lambda plus 2, lambda plus 3, and lambda minus 4, lambda plus equals to 0. So if it is triangular matrix, then with the help of these diagonal elements, we can directly write the characteristic polynomial. Okay, after solving this, we will get lambda equals to negative 1, negative 2, negative 3, and negative 4. So all are negative. So by this definition, it will be negative definite, case 2. Case 3, we are having a matrix. Okay, so the lambda values are 1, 0, and minus 2. All are positive, greater equals to 0. At least one of them is 0. So that is positive semi-definite. Similarly, if we have the fourth case, okay, so all are negative, at least one is 0. So that is negative semi-definite, case 4. In the case 5, these two are positive, but the third eigenvalue is negative. So some are positive, some of them are negative. Then this is the case of 5. Okay, this quadratic form is indefinite. So we'll try to find one example. Okay. Reduce the quadratic form, okay, to its canonical form and discuss the nature and discuss its nature. We have to mention here also that canonical form also mention the matrix of transformation. Also mention the matrix of transformation. So what we are doing, the quadratic form is given. There is no square terms. Okay, x1, there is no square terms. So the diagonal variance will be 0. And these are the half of this one. This A12 will be half of this one. So similarly, we find the coefficient matrix. Now we find out the eigenvalues. So once we find the eigenvalues, we can directly write this one. Okay. So this is our canonical form. This is the required canonical form. Note that in the quadratic form there were no square terms. Okay, there are no square terms, but here there were mixed terms. But here mixed terms are removed. Mixed terms. No mixed terms will be there in the canonical forms. Okay. Since it is a sum of squares, so we will have x square plus y square plus negative 2 z square, sum of the square, and no mixed terms will be there. Okay. And the corresponding p will be find by we have to find the eigenvalues, eigenvalue and eigenvectors. Then we normalize the vectors and we find this P matrix. Okay. Now, since the eigenvalues of this matrix are, some of them are positive and some of them are negative, so it will be indefinite. The nature of this quadratic form is indefinite. We cannot find. Similarly, if we find another example, if we try to find the nature of the quadratic form. So here only one question is there. Okay? You just need to find the nature. You don't have to find the canonical or some other thing. So it is sufficient to find the eigenvalues. Okay, if something is not written, we don't have to do it. Okay. We have to find out the nature of the matrix only. So it is indefinite because some of them are, one is negative, two are positive. So for your practice, I have given some 6 examples. Okay, whether they are indefinite, positive, definite, semi-definite, answers will be. Also find the canonical form. That means whenever you are asked to find the canonical form, okay, x square plus b, not canonical form is lambda 1 x square plus lambda 2 x square plus y square plus lambda 3 or z square. Okay, then you must write the P matrix. Okay, otherwise it will be incomplete. P matrix alpha 1, alpha 2, alpha 3. Matrix of transformation. Because suppose this is not mentioned. Okay. Suppose this is not mentioned. Okay, it is only saying that find the canonical form. Okay, suppose this, okay, the problem was given like this way. Find the canonical form and don't find the P. Then one can write also that since we have found the eigenvalues, so you may be thinking that whether we have to write it the canonical form minus 2x square plus y square plus z square. So, okay, is it a canonical form of this given matrix, of this quadratic form? The answer will be yes, because then you have to select the P matrix. Okay, here the first column will be lambda equal to minus 2. That alpha will be related to this one. Okay, it will depend on the selection of the P. Okay, what will be the canonical form? It will depend on the P matrix. So if something is not mentioned, then you have to realize that okay, we have to find the P matrix also. If it is saying that you have to find the canonical form, then it is hidden that you have to find the P matrix also. Okay, the associated P matrix. But if the question is just to find the nature of the quadratic form, then it is sufficient to calculate the eigenvalues only. Because from here only we can define whether it is positive definite or negative definite, positive semi-definite, or some other else. So we can conclude from here. Okay. So this is up to our minor 1 syllabus. So if you are having any question, you may ask me. I think Swati is asking that whether I can share the PPT or not. I don't know whether you are seeing the LMS portal or not. After every class, I will upload the PPTs. Okay.